the blood flow, it's this globular shape. But as it goes through a stenosis or elongational flow, which is a term often used in polymers, these globular proteins actually stretch out and form strands that expose a lot more bonds to these platelets. And also these proteins can then start self-associating, and so you end up actually with these rope-like structures very similar to what exists on an aircraft carrier that can then catch these platelets as they're coming through these regions. This protein can also stretch out under very high shear stress. And so we found actually that if you take out von Willebrand factor or stop the bonds between von Willebrand factor and platelets, you don't get that thrombus formation anymore. Also, platelets have a natural viscoelastic response when they stick down to these regions of high shear stress, where they'll deform initially, and then if you take off the load, it will retract back down slowly. So that reduces the instantaneous stress experienced by the bonds between the platelets and the surface initially. The platelets also can actively contract back down on the surface, and once it's on the surface, it can form a number of bonds and more firmly adhere them. So, as I've indicated in these previous slides, shear stress can be quite problematic to thrombosis and blood clot formation. So there's other ways we can modify shear stress besides working with these mechanical valves. So instead we can look at polymeric or textile valves that have more natural hemodynamics similar to the native heart valves found in our body. But instead of biological material, these types of valves can be engineered for durability and can also be implanted through fairly non-invasive surgery by crushing down the valve and putting a catheter into your heart and releasing the valve at the location. So we're also looking at a number of these types of valves. So that's a lot of the research I've been doing with Prasad here at CSU, but I'll talk about research that I'd like to propose doing. So I'm interested in continuing some of this embryonic heart development work. So as I mentioned, approximately 80% of heart defects come from an unknown source that we think is through a mechanical environment. So to better understand this environment, we're interested in obtaining 3D reconstructions of flow. So you can imagine if you only have a 2D plane, it's fairly limited information to then characterize wall shear stress and pressure, and then therefore the response of the heart to those changes of wall shear stress and pressure. So in addition to with this 3D information, we can also look at multi-scale changes in time and space. So we want to monitor single fish from early on in development to later stages in development as we perturb the mechanical environment. In addition, I'm interested in looking at manipulating flow in this environment more acutely as opposed to the systemic approach I described earlier. So by doing that, we can look at very specific mutations, or we can look at the application of drugs, or even surgeries where we can surgically modify parts of the heart to modify flow. In addition, I'm interested in actually obtaining biomechanical measurements of the heart as it's developing at various stages, and what happens with that development as you perturb that system. So the plan would be to remove the heart from the zebrafish and actually place it into an experimental device where you can control the stretch and pressure inside the heart to then estimate what the mechanical properties of the heart is at different stages. This is commonly done with mouse arteries and is also now being done with lymphatic vessels, which are actually a similar size to the developing heart. So I believe this is a very doable approach. In addition, to gain some more insight into the pumping mechanics, I'm interested in the computational model of the pumping mechanics. So with that, I think there's researchers here at CSU that can provide some collaboration in the computational modeling. In addition, with biophysical measurements, Diego Croft has a number of imaging tools and optical tweezers that can be used for biophysical measurements in the zebrafish. And then also continue work with Deborah Garrity, who's an expert in developmental biology. So with this work, I think, so right now we have a grant, an NSF grant that we've applied for and we're waiting to hear back about. And then there's also an American Heart Association grant that we've submitted for this work. I believe once we can show a very specific response of the heart to changes in flow, and we can start to propose maybe the application of similar techniques to then modify flow in embryo to then potentially mitigate the risk for congenital defects. So if we can do that, then I think the NIH would also gain some more interest in this, but initially the application to human health is, isn't as clear for the NIH. In addition, I'm interested in a diagnostic tool to assess the bleeding risk of a patient and also the thrombotic risk of a patient. So many people with a bleeding disorder go unnoticed with the bleeding disorder until they get older and have a severe accident, when suddenly the bleeding disorder can become life-threatening. So if we can have simple diagnostics to detect these bleeding disorders more early on, these patients can understand what treatments they can receive in order to reduce the risk of their disorder. So to develop this diagnostic tool, I'm interested in using a series of microchannels that test different parts of this blood clotting process. Again, I'll spare some of the biological details, but one of the focuses too will be on changing the flow environment, so looking at stagnant flow, coagulation processes, and then also channels that will focus more on these high shear stress responses that we saw with these mechanical heart valves. So since these are high throughput systems, we can also look at drug dose responses and a number of different things in the lab much more quickly than what can be done currently. Also, there's no current tool that clinicians have that studies how blood's responding to changes in flow. So if we have these micro channels, we can then also provide clinicians with a tool to look at how blood's responding to these high shear stress environments. And then I'm interested in evaluating this response with either systems biology models or neural networks to then look at the synergy of some of these different stimuli in these channels. And then there's a number of potential collaborators here at CSU for this project, including Melinda Fry, who is a hematologist in the vet department, and then also David Dandy and Charles Henry, who can provide some input on microfluidics. And then Shrik Prasad is expert in systems biology modeling, so he could be quite helpful with the modeling side. And then my current supervisor, Jorge DiPaolo, down in Denver, is a clinical hematologist, so he can provide patient-specific blood for this device. In addition, I'm interested in development of a multi-scale model that can predict thrombus growth. With a multi-scale model of thrombus growth, we can look at the potential of thrombus growth in different medical devices and also different diseases. So for example, if someone has atrial fibrillation, they're at risk for blood clot formation, but only specific patients that have it, and I believe that's due to the changes in fluid mechanics. So if we have a model of thrombosis, we can apply that model to the flow environment to then predict whether that patient's really at risk for thrombosis or not. So this model would involve transport of cells in it and also transport of chemicals that could stimulate these platelets and cause coagulation. And then in addition, I want to use this model to then focus on the development of specific medical devices that are implantable in the cardiovascular system to then guide the design of these devices, so such as prosthetic vein valves, vascular graft, transcatheter mitral valves, which are a hot topic in the NIH right now. and also in looking at development of new stents based on the predictions of the thrombosis model. And I'm also interested in maintaining work on development of some of these medical devices. So I think these projects are really good for master's students because most of them will have an interest in going to industry, and these devices will help them get a leg up and getting a position in industry. So with the development of medical devices, there's a number of biomaterial experts around CSU, including a number of people in this room. In addition, there's computational modeling experts that can provide quite a bit of support on the multiscale model of thrombosis. And then also there's clinical collaboration. So Chris Orton is a surgeon over in vet school, and he can actually implant some of these devices to then look at the response in the body, which is a big advantage we had at CSU, because if you're over in the hospital, you can't just randomly implant devices into people. So, and then also I'm interested in collaborating with Gary Lucassen, who's also here in Fort Collins, and provide clinical support and actually patient-specific images of coronary arteries to apply this model, and also of heart arrhythmias. And this funding for this project can come through the American Heart Association, National Institutes of Health, and also for the medical devices, the National Collegiate Inventors and Innovators Alliance provides money to look at new medical device technologies. So here's just a real brief timeline to give an idea of when we start applying for funding for some of these projects. So in terms of cardiac development, I already have 2 grants that we're waiting to hear back from. In addition, there's a number of grants I had in my mind that we could submit for this work, so we could start submitting those right away. In terms of the microfluidic diagnostic device, I'm actually working with a PhD student right now down in Denver, and they're looking at specific microfluidic channels to assess a bleeding disorder that you get when you get these medical devices implanted. It's known as acquired von Willebrand syndrome. So I think we could start applying for grants to look at these very specific applications of the device to begin with, and then eventually I'd like to get a more general device that clinicians can use. And so we can start applying for funding right away with that. And then for medical devices, I'm looking at getting a master's student to then start looking at developing this model of thrombus transport, and then start applying it to medical devices. And then so we can start applying for funding after that. So I have a bit of grant writing experience in the past. So currently I'm on a fellowship with the National Institutes of Health, postdoctoral fellowship. And then also I have a pending R01 that I put in for the that we've put in for super hydrophobic mechanical heart valve work. I also have a pending American Heart Association grant with Deborah Garrity on this developmental biology, and then also another application with the National Science Foundation. Prior to that, I was in Australia, and I've submitted grants to the Australian Research Council, grants that I've developed from scratch. And the Australian Research Council is very similar to the National Science Foundation. And then I've also contributed to a number of successful grants to the National Health and Medical Research Council of Australia. And that's very similar to the National Institutes of Health, and the competition there is also quite similar to the US. I have a number of friends that are having quite a bit of difficulty getting funding there. And then I have some experience with the NCAA as well for developing these medical devices. So really the mission of my group would be to prevent and treat cardiovascular disease through fluid mechanics. I have a basic science approach as well as a translational approach of developing medical devices. Eventually I'd like to get a little bit more into biological locomotion, lymphatic flow, pulmonary flow, reproductive flow, and then also bio-inspired design. I know the course experts here are interested in pulmonary and reproductive side, so it's definitely an area I'd like to get more into. In terms of teaching, Really, my expertise is in fluid mechanics, with also a fairly strong background in solid mechanics. So I'm fairly comfortable teaching any of the fluid mechanics courses, especially biofluid mechanics, heat mass transfer. And then in terms of biomedical engineering, there's a number of courses that I'm interested in teaching, including transport phenomena, which is similar to fluid mechanics. Also problem-based learning, biomedical engineering lab, biomechanics, biomaterials, and quantitative systems physiology. So in addition to courses that already exist, there's a number of classes, or 2 classes specifically, that I'm interested in developing. One is a cardiovascular biomechanics course, which would be at the graduate level. And in this course, it'd be really looking at modeling transport in the body, specifically transport in lymphatics, cardiovascular, and pulmonary system. And then in this course, at least a good portion of it will also be focused on soft tissue mechanics. So this involves large deformations, so it requires continuum mechanics expertise and constitutive modeling to model deformation of these soft tissues. And then the small component will also focus on what's happening at the cellular scale, which is important for understanding what's also happening at the larger scale. In addition to that, I'm also interested in working on a medical device course where students can look at what happens when they go to industry in terms of regulatory processes, patent processes, and then also what it takes to develop a company around these medical devices. And this would be a useful course for actually attracting students to my group for looking at developing medical devices, and then hopefully these students will go on to then develop their own companies around these devices. And I have some experience with a similar course when I was at Georgia Tech, where I developed a software program where students develop a simulated company. They pick how they might have competitive advantages over other companies. They then apply focuses during different years of the company development, and then apply a budget to these, and then they get a report back to see if they're making good progress with their company. So for example, if you focus just purely on firing your first year, the company's not going to succeed. So this was kind of a useful tool that the students were able to use to better understand what it takes to start a company. So with that, I'd like to acknowledge a number of collaborators and mentors that I've had over the years, especially a number that are here at CSU, and then my PhD advisor, David Koo at Georgia Tech, some other departments here like Deborah Garrity in the biology department, and then Jorge DiPaolo, who I'm currently working with, and then a number of scientists I worked with in Australia and New Zealand. So with that, happy to take any questions. Yeah.
Thanks a lot for the talk, really enjoyed it. I was wondering
My pleasure.
about your the surface coating on your heart valves.
Yeah.
Is that like what kind of a lifetime does that have? Does it wear away? Does that degrade?
So that is the biggest concern with these coatings is it does wear away with the current coating we're applying. So with Arun Kodo, we're looking at developing new technologies that are much more durable. And one way to do that is really to apply these textures within the material itself. Potentially, it could be more durable than applying a coating. Yeah.
You had that picture with the applying drugs and other thrombosis versus bleeding.
Mm-hmm.
Is there a time lag that's known where you can move back and forth between those two things, or is that just sort of is there a hysteresis effect that you can't move back towards one or something like that?
It would depend on the drug, and I don't know exactly what that time lag would be, but I know like in the case of some anticoagulants, you have to go in for weekly checkups when you first start getting it, because you can go such in a drastic direction of getting bleeding risk versus thrombotic risk that the doctor has to see you fairly constantly. And so that's where a microfluidic device again would become very useful, because the doctor could just put the blood in the device and see where you're at and get an instant response and modify the drug as needed.
Sure, thanks.
Yeah. You're first.
So on the same lines, do you visualize this device? So you just mentioned that this is for a doctor. Do you think there is a possibility for a device where a patient just keeps it with
Yeah.
him or her, and then would there be a quick way to know if they are at bleeding risk or?
That would be the ultimate aim. One of the risks with giving it to the patient is it's a patient and they don't always follow what they're supposed to do. But with this device, one thing I didn't mention is I also want to make it so that it can be used kind of standalone without microscopy or anything. So with that, I want to apply some LEDs on one side and a CCD on the other side to then read out the thrombotic response. So in that case, yeah, you could probably give these to the patient, have them monitor their own blood, and then maybe get quicker responses rather than waiting a week to hear back from the doctor. Yes?
I was interested in your, the little valves in your legs.
Mm-hmm. Yeah.
So you said you actually worked on prosthetic versions of that? What were
Correct.
they made out of?
Polyvinyl alcohol?
Oh, like a permanent valve, or was it a degradable thing? Or?
No, it was meant to be a permanent valve. It did have thrombotic problems, which is kind of what stopped that research, but I think with a lot of the experts here,
Right.
we could potentially develop ones that aren't thrombotic.
So you got them to mechanically function and figured out how to implant them?
Yeah, so they would open with minimal pressures, which you need in the venous system, and then they would close quite readily as well, so that you don't build up
Right.
pressure. But really, the problem ended up being thrombosis.
What kind of a animal model did you try them in
Sheep.
there?
So I was actively involved in the trials with the sheep. So we put it in the jugular vein, and the idea was that the sheep would go down to eat, lean its head down, and so the valve would open, and when it's up, it closes, and so there's that back and forth. Not quite as good as having it in the leg, but
Right.
that's the best we could do.
Well, the work with the zebrafish sounded interesting.
Yeah.
The technique that was built. First, is that something you developed or they developed? And then secondly, is there a way to use that to do some more of the kind of studies that you might be interested in?
Yeah, no, that's a good question. So this was actually developed by Brennan out of Prasad's group. He was a PhD student. It's nice because you're not actively invasive on the zebrafish. The downside is it's hard to really understand what changes are happening as the zebrafish is in the centrifuge, and it's a systemic force that's felt throughout the body, whereas it would be ideal to create an acute injury or acute modification to look at how the heart's responding. So I think it'll still be useful, and it's providing us a lot of insight into the mechanics right now, but I'm interested in applying a more acute problem.
Move away from that.
Yeah. And one maybe fairly non-invasive way would be a laser injury, so injury the myocardium at very specific locations with a laser. So you don't have to poke in, but you're looking at a number of different ways. Yep.
Very nice talk, Dave. I particularly like that the thrombosis diagnostic thing.
Yeah.
That idea is really cool.
Very cool.
So I do have a couple of questions. With the diagnostic device, can you tell me what you're expecting to read out?
Yes, absolutely. So there's really two readouts that I think could be useful, but I think I would lean more towards looking at the thrombus growth or potentially even occlusion of specific channels. So there's two different ways you can monitor that. You could monitor the pressure drop with respect to time or flow. And if it occludes, then obviously you don't have flow anymore. And the pressure drop goes up dramatically.
So I'm thinking more from the patient perspective. If you just hand it to a patient,
Yeah.
what would he or she
Would the readout be? Yeah, so they would just basically get, so hopefully by that point, we'll have the systems biology approach or neural network, depending on what way we go with this. And so that essentially, depending on how these different channels are reacting, the readout would be whether or not you need to use a specific drug that attacks the ADP receptors on the platelet, or you need a drug that attacks fibrin formation. And so it can kind of tell you what drug you need and then maybe the dose that you need as well. Because as I mentioned, you can have multiple channels that use different doses to then look at what dose you could need.
And moving to the microfluidic device that you showed, you showed an image of some channels and things like that.
Yeah.
What size scale are we talking about?
Yeah, no, that's a good question. So I'll explain as we go, but the width of the channel is 300 microns, and the height of the channel is about 124 microns. If you get below 100 microns, blood viscosity starts to change, and you're also getting on the order of red blood cell diameters, and so it's more difficult to understand what's going on from a rheology perspective. So I wanted to keep it above 100, which is why it's about 100. The gap, as it closes down, is actually only 30 microns, and so that's where I guess I'm kind of surpassing that limit I set.
So there, wouldn't the shear stress be so high that these would be ruptured or cause?
Well, the rupture shear stress is actually fairly controversial. So if you have a synthetic surface, rupture is appearing to be more likely versus if you just have blood cells suspended in flow. Looking at the red blood cells after they go through these channels, they're still fully intact. We've also checked to see if there's any hemolysis, and we haven't noticed any hemolysis. Right now, we're blocking platelet activation, which I won't go into too much detail in the biology, but we're also not mechanically activating the platelets at that shear stress. But that is the stress that's experienced by these mechanical valves at these gaps. So even FDA-approved valves.
So final question. This is related to how you were relating the pressure drop to the rate of contraction.
Yeah.
Slides.
Yeah.
So I'm thinking about the pressure drop and the rate of contraction. It's, to me, it seems, wouldn't you think it is, sort of obvious that as you constrain the tube,
Yeah.
obviously the pressure drop would go up.
Oh, for sure, yeah, the viscous
So
losses.
that's, right, that's sort of obvious. So
Yes.
what additional physics are you gaining from studying this? I mean, saying that delta V is proportional to some sort of a contraction is pretty obvious, I think.
Yeah. No, I think as engineers, we think that's fairly obvious. It's not as obvious in the biology side of things, so it's still useful information for some of the biologists. But what we're gaining more insight into really is what in the structure of the heart is allowing it to either contract more quickly or less quickly, and that's where I think we're really going to be able to start understanding how some of these congenital heart defects could start coming from.
Great. One quick one, a completely different direction.
No
So
problem.
you mentioned the entrepreneurial course that you thought you wanted to develop,
Yes.
but you've had experience with it in Georgia Tech.
Right.
You've taught students here at CSU.
Yes.
What do you think would be different about the populations, or what do you think would make it possible to do, or have you experienced a bunch of undergraduates here that would actually do well with it?
So working in Prasad's lab, he had a number of senior design projects focused on medical devices, and I saw an enormous interest in that area. And so I think that there'd be quite a few students that are interested in it. And I don't really see any difference between that and the students at Georgia Tech. So I think it could be quite a successful course. And as I mentioned, I've got my own personal motivation because I think it could attract students to my group.
I thought you meant to say that our students were better than them.
Oh, sure.
That was not required in there.
All right, thanks, Steve.
Thank you.